Right, so yeah, so during lockdown, I got hooked on watching this chap on YouTube solving Sudoku problems. And with a normal Sudoku problem, you have to have at least 17 digits in the grid you start with in order for there to be a unique solution. But with the problems he looks at, he adds extra constraints onto the problem, which means you can start off with a lot less digits. So in this case here, there's no digits on the grid to start with at all. But there's an extra rule that, so on a normal puzzle, you have to have the numbers 1 to 9 in every row, column, and box. And he's got an extra rule in this puzzle where each of these sort of sub boxes also add up to the same amount. So you can see there's quite a few of those on there. Yeah, so the trick to start with this puzzle is to look at this center box. So you can see you've got 4 of these boxes. And because you know you've got the digits 1 to 9 in the middle there, 1 to 9, if you add them up, you get to the number 45. So the total of that box must be 45. So you've got the center digit plus 4 lots of that digit down the outside. Hopefully that makes sense. Which then means the center digit can only be a 1, 5, or 9. So if the center digit was 1, you'd have 44 around the edge, so each of those would add up to 11. Okay, so I'm just going to play a couple of minutes of this video, which will hopefully make some sense in the context in a bit. And it doesn't matter if you don't follow it anyway. Finding my mouse is the...
So that is what we can immediately say, and that gives me a hint, I think, into how we're meant to approach the puzzle. Because the interesting thing about the cages now is whether the central digit is 1, 5, or 9. So whether the cage totals are 9, 10, or 11. There are sort of 4 flavors of dominoes that will work for each of those options. In other words, a dominoed cage can only be one of 4 different types. So imagine this was a 9 in the middle. Then we know that the cages here are going to be a 1, 8. There's going to be a cage that's 1, 8 if it's a domino, a cage that's 2, 7, a cage that's 3, 6, and a cage that's 4, 5. If this is 5, there's going to be a cage that's 1, 9, a cage that's 2, 8, a cage that's 3, 7, a cage that's 4, 6. And if this is 1, and we're adding up to 11, it's going to be a 5, 6 cage, a 4, 7 cage, a 3, 8 cage, and a 2, 9 cage. So there's only those sort of 4 options. So I think what we're probably meant to do is to colour the cages. So, I mean, these are the big decisions that we're going to be faced with, aren't they? So let's do that. What colour should we make these? We'll make that one orange. We should have probably a blue cage in here, shouldn't we? Should we have a green cage? And maybe a purple or a grey or a yellow? No, yellow's a bit boring. Let's have purple. Okay. Or we could make the middle purple, actually. Let's make the middle purple. That stands out rather nicely. So this digit can never go in a... Ah, no, that's not true. I was going to say it can never go in a cage, but it can't go in a domino. That is true. Yeah. Oh, no. So when I said yes, I meant no. I was suddenly thinking, okay, in this box here, because you can't put this digit in a domino, because the dominoes only have 4 different flavours, never including this digit, whatever it is. It's going to be in one of those squares. But look, this isn't a domino either, so we don't actually... Well, it is a bit restricted in box 6. Can't go in a domino. That's a domino. So it's in one of 2 places. There. It's there. That's where it's got to go in box 4 by Sudoku. It cannot go in a cage. So, there we go. Look at this. We're going to chase this purple digit around the world. Well, nearly. Actually, nearly. Let's keep going with this, because this might do something. No. We're going to have 4 cells. I'm a bit reluctant to pencil mark 4 cells. And the box 3 looks entirely underwhelming, doesn't it? Okay, so maybe we've got to... Maybe we've got to think hard. Yeah, okay, look at row 6. That's interesting. So, these horizontal cages here can't be the orange variety, because if they were, this cell couldn't exist. So these have to, they obviously can't be green, so these have to be blue and grey, and this must be orange.
Right. Okay, so that's it for now. So the point here is, so normally when you're solving the puzzles, you're working out where the numbers are going. But he's going a level above this, so he's working out, he doesn't know what numbers these are, but he's working out where those numbers can appear in the grid. So what he's done here, by using colour, he's added extra information into the grid to solve the problem. And then he keeps going with that, and eventually he fills in all the squares, and he works out what colour each of the squares were or are, and then once he's done that, he can skip on a bit. Yeah, he can then just replace the colours with the actual numbers they are.
To 11, don't we? So all of the A's must be 2s to go with this.
Okay. Yeah, so the point is he's adding extra information into the puzzle in order to solve it. So we're done with Chrome. Right, okay, so then on to the talk. So as Kevin said, I wasn't originally going to give this talk tonight, so you're going to have to excuse me a bit. So I gave this talk to an Accu York group, I think it's the end of November. So they're more of a C++ sort of group, so, but I don't think that's going to matter too much. So a bit of a disclaimer anyways. When I started off with this talk with just a title, and then thought, there must be some interesting talk you can do around type systems. And then the more I researched it, the bigger the topic I found it was to be. And so then I decided, well, I'm just going to sort of pull out what I think are the interesting parts about types and how different languages treat them in different ways. So we look at quite a lot of languages tonight. I think if there's time, which there wasn't last time I overran, I think there's 16 different languages we look at. But the only one I'm really an expert on is C#. I don't really know too much about quite a few of the other ones. But please ask questions as we go along, and we want to be a sort of an interactive session if we can. The first idea I had was I'd come up with all the terminology around types and then describe what they all were and then look at them in each language in turn. But I couldn't really make that into an interesting talk, so I thought it's more interesting if we just look at a language at a time and then just introduce the types or the terminology as we go. So I think, a good place to start is actually what do we mean by types, what are types, and I probably have asked you all around the room what your definition of the type is. I get a different thing from different people. But for the purposes of the talk, just so we've got some sort of common vocabulary, we've got primitive types. So primitive types are the things which are built into your language. So they can be like strings or date times or maybe booleans or numbers of some description. And then from these primitive types, we can then create complex types. So that one there, that's made up of a name, address, and a date of birth. And then we can give those complex types a name, so that then becomes a type alias. So for C#, that would be more like an interface than a class. So a class has got actual code along with it as well. This is more an interface of how something looks. In Swift, however, they call these named types. So even basic things like this have different names in different languages. So the first language we're going to look at is assembly language. So hopefully can you all see the screen okay from down there? Okay, yeah. So I've made up some assembly language here, which is you take the number 1, 2, 3, 4 and you move it into a register. You take the number 5, 6, 7, 8, you move it into a register. You add them two together and put the result into a register. And then you look at the location of that memory address and just do something with it. But the problem is here is we're moving these numbers around and we're adding them together and then we're using them to look at a memory location. And we don't really know whether that's a sensible thing to do. We don't know whether that's going to represent a valid memory location or not, or whether it's going to do something that's just going to crash the program. Because all we have is just some numbers. So you might think, well, yeah, maybe with this information we can work out what things are numbers and what things are memory addresses by how they're used. So we look at some examples. So it makes sense if you've got two numbers that you're allowed to add them together. You can add together 65 and 2. That seems a reasonable thing to be able to do in your program. But if you've got two memory locations, I'm just using that to represent memory, or two pointers, it probably doesn't make sense to be able to add two pointers together because you're adding the location of this part of your memory with this one, and you're just going to get some number. So that probably doesn't make sense. But what about adding a pointer to a number? Does that make sense? Well, that would make sense because you can advance along an array by doing that or looking at some different data. What about adding the number 2 to the ASCII value of a letter? Does that make sense? Yeah, because it gives you the next letter in the alphabet. Okay, or by one. What about ORing it with 32? Does that make sense?
It worked.
Yeah.
There wasn't a question.
Yeah. Yeah, so that would actually make a letter lowercase because it's just the way ASCII numbers are apart. But from the point the computer's point of view, it's just seeing that you're doing 65 plus 2 in those first 4 examples, and so it doesn't know what you just asked it to do makes sense or not. So in assembly language, we don't have very much information at all. All we've got is some numbers, and that's it. We've got no idea. We can't help the programmer, if they're writing assembly language, know whether they're doing anything sensible, and at runtime, you haven't got any idea either. So, why do we care about all this? Well, the last thing you want to do is when you're running your program on a customer site and you get some runtime error and it crashes and your program looks bad and it looks bad in front of the customer and it's going to be expensive to fix and so on. So the one thing you don't really want to have is runtime errors for your program. So what's better than a runtime error is that you have unit tests during your build process and your unit test fails, and then that problem doesn't happen when it's in production. But better than a unit test is if your code just doesn't build in the first place. So you can't build your code, so you don't have to run the tests. And what's better than your code not building is if your IDE can tell you, as you're coding, it puts a red squiggly line underneath something or a green line saying this is not what you want to do. But better still than that is if you can't actually write the bad code in the first place, in that functions have got the correct names and the correct arguments and everything. And so by writing your code, you're going to do the right thing and you're not going to get it wrong in the first place. And types can help with the build errors, the IDEs, and also this pit of success. My quality diagram here. So if you think of a modern compiler these days, you feed in your source code and you no longer just get the compiled binary out. You also get things like autocomplete and tooltips, using the language service protocol, and you get rich errors and warnings and diagnostics about what's going on. So modern compilers are quite advanced, and they do that using types. So the first language I learned to program was BBC Basic on a sort of an Acorn Electron, so that's going to be the first language you're going to look at tonight. So I programmed in this for years and years and years, and then I came to prepare for this talk and I realised I could remember none of it whatsoever. I thought I monitored that. So how many of you have done sort of BBC Basic in the past years? Yeah, exactly, that type of era, yeah. Okay, so don't know if I can zoom in. Okay, so 10, that's our line number. So because you didn't really have IDEs back then, so you had line numbers which you could edit. So you can type something like age equals 49. So that's going to create as a new variable called age, and we can print that. Oh, I have to run it, of course. And we get 49 back. Okay, and then, okay, so say we're going to create a variable called name. On that. And we can see that doesn't work. So we can't just assign a string to a variable like that. So instead we have to name it with a $sign on the end. Oops. Yeah, and then when you use it, you have to have the $sign as well. Okay, and that works. So we have a former type in that, it knows that's a type of some sort of number, and that type is a string. And we signify that with the $sign. My notes. Yes, so we can also do so we can also got a %. %. Yeah, so we can see that actually B% is actually integer. So we've got 3 different types there. And we can also do arrays. So B is an integer, isn't it? I think. Yes. Yeah, A is a float or some sort of decimal value. Yeah, and you've got arrays as well, so you can do that. And there's 0. Double switch box. Yeah. Right. I'll copy the rest of the text. I can't cope with the mouse going the wrong way. Right. That's gonna. Yeah. So here we've got procedures or subroutines. So this is a subroutine called display where I pass in a string, and I call it up there. So the name of the function, subroutine, and then you also have functions. So subroutines can't return values, but functions can. And they start fn and then equals and the thing they're going to return. So there's a naming convention here in that it's procedure underscore or function underscore that says what it's going to be.
So what happens when you put a number into a string and then try and operate on it?
Oh, you get type mismatch error and all sorts of things. Yeah. Yeah. So the point is there's naming conventions which are used and. So in some sense you think that seems a bit sort of almost backwards, but even today in React you have naming conventions for things such as, if you've got a custom hook, I don't know, many use React, but that has to start with use and undercase, and if you're making a component or not, the first letter has to be in capitals or not. So it's... So yeah, and so in terms of types here, obviously we've got variable names which they're using to also encapsulate the type. So without any types, so you haven't really got any extra help to the user or the IDE or anything. So we've seen one solution was to have the $sign on the end of variable names. So what else did we do before we had IDEs? Well, we had Hungarian notation. So in Hungarian notation, the beginning of the variable name, so the prefix also tells you some information about the variable. So looking at height, or looking at count there, it's an n, which in this case means integer. And then you've got more complicated things. So you've got floats, you've got was that a null? Well, strings, booleans. So B for boolean and SZ for string. But the problem was people came up with some quite complicated conventions. So this example here I found was a constant reference argument holding the contents of a database column last name of type varchar 30, which is part of the table's primary key. So obviously you can look at that and in theory get quite a lot of information out of it. But the problem is, this isn't enforced. So in this example here, I've said n count equals true, where n we've said means integer. So we've named it the wrong thing. And the compiler doesn't care. So it's something that can aid users, but it's not going to help the compiler, and it's not going to help in the IDE. So then what we have these days is we have type checking. So, you all use it where you declare a variable type string, you set it to a string and it's happy. You set it to a number and it's probably going to complain. So that's type checking. And then that goes hand in hand with type inference. So, with type inference, you're not telling it the type, you're saying it's going to be a variable called name. I'm setting to the value David, and it then uses inference to work out that sort of type string. And if you look at how inference works, there's like a whole loads of maths and theory behind it, and you get these complicated rules like this. So, this rule looks, certainly to me, looked quite scary the first time I read it. So what it's trying to tell you there, it's given these stuff that's true on the top of the line, you can infer what's true on the bottom of the line. So again, that probably still looks quite complicated. So we do a sort of a simpler example. So if you're writing your own type inference, you'd naturally do this anyway. This is sort of just like the theory behind it rather than anything else. So who wants to be the part of the compiler then? You don't want to? Okay. Okay. So I'll give you this here. So what's the type of A? Very good. Okay. Type of B? Okay. Okay, so now you don't know.
String. Well, no, because I assume C is other variables defined elsewhere because it's not surrounded by single.
Yeah, okay. I don't know where that message is coming from. Is that you? Okay, yeah, so if I give you this next example, now can you tell me?
It's an integer.
Yeah, exactly. So the point here, to infer the type of something, you also need to know what else is going on in the world. It's not just that one statement. You need to know what else is in your universe of stuff. And if you go back to this bit here, that's what that first symbol means. It's given this knowledge of things already. That funny sort of T thing. Okay, more complicated example.
So E is an int, F is an int, G is an int.
Yep, it is, yeah. And so the way you did it is exactly like that. You worked out, the type of the various bits first, and then.
No, I didn't. But that would be something.
Yeah. Pretend you did. Yeah, pretend you did. So, in your head, you probably build a tree, and you didn't realise it in your head of saying, what's the first bit, what's the next bit, and then what do I get if I combine the two together? Does that make sense? Yeah. And so it's quite fortunate that. So you've got rules like that. So you take two ints and you subtract them, and two ints and you times them, and then if you add them, you end up with an int. And if you think about when you're building a compiler, the first thing you do is you pass your language and you build a syntax tree anyway. So you've already got this structure of data. So actually determining the types at that point is actually relatively straightforward. Okay. So any questions around that? Because that's the whole of type theory in about 2 minutes. So does that make sense to people? Yeah, okay. Yeah, so I have written simple parsers in the past not knowing this, and this is just like naturally how you do go about it anyway. Now, so the next thing is type coercion. And so this is when, you're doing an operation with two types, which you don't necessarily, the types are different. So in that top example, you've got 12 plus 10, where 10's a string. And then, you've got a Boolean plus an integer, and you've got a subtraction going on. So the question is, are these things valid? And the answer to that, it depends on your language. So in C#, the top one works and the bottom two don't work. I'm going with yes, but I can't remember. yeah, I could believe that, yeah. And then in JavaScript, yeah, it would be 1,210. So, yeah, so JavaScript. So before I gave this talk, I used to sort of hate JavaScript. Yeah, I think hate JavaScript was a good term. And I didn't understand all these weird rules and all this weird stuff with types all going on. And then, so then I researched JavaScript as part of this talk, and I actually quite like JavaScript now. Now I understand there is actually logic behind it all. Yeah, actually, you know, I don't know. I still use TypeScript, but yeah. So.
Explain the logic behind adding 1 to true and getting 2. I mean,
Okay.
I know technically how it's working, but
Yeah.
why should?
Well, we'll go through it now.
Okay.
Yeah. Okay. So. Yeah, so in JavaScript, you don't have many primitive types, Boolean, numbers, strings, and then you've got a few special ones such as null and undefined, and then more recently, you've got big ints and symbols as well, but most of the time we only really care about Booleans, numbers, and strings. And so JavaScript is what's called dynamic types, which means the types are checked at runtime rather than at compile time. And they can also change because it's weakly typed. So in this case here, you know, we declare foo as a number, and then it can change to a string, and then it can change to a Boolean as you're using it. And that's fine in JavaScript. Yeah, and because it also has types as it needs to, we say it's weakly typed. The definition of weakly typed isn't really agreed upon between different languages. But here we just mean it allows it to be converted from one type to another. Oops. Yes, so I need to open mode. Hopefully I can zoom in bigger. Right, hopefully it's big enough. I'm just trying to know what it is I'm actually demoing. Yeah, okay, so we're looking at the rules in JavaScript to work out how types get converted from one form to another. You've got primitive types, as we said before, and other types such as objects and arrays. And you only really need to remember the rules for primitive types. So for everything else, it always tries to either tries to extract its value from it, or it converts it to a string. So if we look at a I hate Apple Macs. Right. Okay, yeah, so we look in an array, for example. 1, 2, 3, dot. 2 string. Okay, yeah, so that's going to try and convert an array to a string. And if you've got an empty array, it gives you an empty string. And if you've got objects, I can't remember, you do objects in JavaScript. Is it like that? Oh, that's a bad example, that one. Well, it has converted it to a string, yeah, it's just not a very useful string. Right, yeah, so that means, so yeah, that converts it to string. So now we only really need to worry about the rules for primitive types. So one of the rules is the bang symbol will convert anything to a Boolean. So if you give it a string, that converts it to true. If you give it null, that converts it to true. So that will always convert things to a Boolean. If you add anything, plus anything, we'll convert it to a number, or not a number. Like so. And then if you've got plus between two things, it will always convert the it to a string, so, because one side is a string already. And then finally, you've got minus. So if you do true minus 2, for example, it converts both sides to numbers. Okay, and it turns out there are actually only rules you need to learn with JavaScript. So that all sort of makes sense until you then get to things such as parse. Don't know if you can read the line at the bottom there. So if you do parse int 1 divided by 0, 19. And then that gives you the number 18 back. So has anybody got any ideas why that would be the case? So what the parseInt function does is it takes a string and then attempts to turn it into an integer.
Is it going to be not a number?
Okay, you're along the right lines. Okay, so its first argument has to be a string, so it has to convert whatever there to a string. So if we look at what 1 divided by 0 is, oops, it's not that. That's infinity. So it's going to pass the word infinity in as a string. And then the second argument to pass in is the number base. Yeah, so it turns out that I in base 19 is 18, and then n isn't in base 19, so it doesn't pass it any further. Okay. So again, it's like, it looks weird and it looks completely daft that it's doing that, but then there is logic behind it, and it is just following a set of rules. Whether or not you agree with the rules it's another matter. But okay, and then so then once you've got all this knowledge, you see, you can then do great things and put that all together. .net. Yeah, so you can then do that to generate a sort of JavaScript to that form where it just follows these same rules again, like not of an array is 1 and so on, and then you can give it some JavaScript and it generates it in this form, and then that's actually valid JavaScript, which you can hopefully run in your browser. So if I paste that in, which I've just generated, it should have opened a box somewhere. Yeah, so it's been opened a box called .net. So again, it's just following all these weird rules which we looked at already. What, this bit? Yeah, you're very right. Yeah, I can do, but yeah, it's not going to.
I suppose if you're just leaving your developer job and you really don't like your employer.
Yeah.
Or you want to type proprietary code.
Okay.
Easter egg on last day.
Yes.
This is not very efficient obfuscating. Okay.
It does make a massive file, doesn't it?
Yeah, it's a huge file compared to this normal obfuscation where you just rename all variables and stuff like that.
Yeah.
Flatten the methods.
Right. So that was JavaScript. So we've got some Python next. What I don't understand is like every time I'm dragging the window off the wrong side of my screen, and I don't know where it's going. It's just it's like I've got another monitor somewhere. But anyway, how do I zoom in here? Oh, it's up here, isn't it?
The same funny key plus.
Oh, is it? Yeah, that's quite. Oh, you're right. Okay, so Python. So this is Python version 3. So by default, Python doesn't have any type checking in it. It's not built into the language. You don't declare the types. So here, hopefully you can read that. I've created a function that takes in a parameter of some type, and I do some calculation on that parameter. And it's quite happy about that. And then I've just created a second function with the same name. This time I've given it some type hints. So they're hints to the compiler. This is the type, or hints to the IDE and the programmer that this is the type of the variable and what it's going to return. And yeah, so you can say I'm encoding it with two things. But by default, none of this is checked, and we've got no feedback. So with Python, you have third-party tools that provide type checking for you, which actually uses these hints. So I can turn that on in Visual Studio Code. So I've got basic or strict or off. So this is just the basic mode. And now things start to get checked in your IDE. So I'll turn that on. So you can see here it's detected that I've got two functions with the same name. And down here it's detected that I'm calling a function and I'm passing in a string when I've said it should be a float. So with every release of Python, the type checking is getting better and better and better as they build more of these type hints in. But they're definitely built on top of the language almost, well, definitely as an afterthought. The base language doesn't have it. And one of the reasons for that is it's a very dynamic language, Python, in that you can redefine functions at runtime and things like that. So you can't have everything type checked in advance anyway. So one of the things I tried, so I can't see the screen myself, it's reflecting. Right, that's better. So, yeah, so you've got, you import the typing library to say what sort of typing hints are available to you. So you can create new types, for example. So here, I'm saying a vector is the same as a list of floats, and I can then use that as a type in my functions. And down here, I'm saying integers are also called address IDs and custom IDs. So here I've got a custom ID, sort of type custom ID and address ID. And then I can use those as parameters to a function. And you can see the IDE warns me that I'm passing the parameters around the wrong way. So a bug I see quite often in my code anyways, if you've got a function that takes two integers as arguments, is that it doesn't have to stop you passing them back to front. So in this case, I'm passing the custom ID where I'm expecting the address ID and vice versa. But if I run this code, you can see the code quite happily runs because this is just a check in the IDE. The language itself doesn't know anything about these type hints. So it's quite happy with the fact that I've swapped custom ID, address ID around. They also have generics, the same, a bit like other languages like C#, etc. So originally in generics, you had to declare the type that was going to be the generic thing, and then you pass it in saying my class stack has a generic of type T, and then you just use it in your methods. And now the new syntax is a lot simpler. You just say the class is of type S in this case. So this is much more like the C# sort of style. So this is just one of the ways you can see that types are constantly improving in Python. And then you've got type constraints, a bit like the where you have in C#, where you can see that it can be anything, or it's got to be inherited from a string, or it can be a string or bytes. I think what other examples you've got. Yeah, you've got a type which is never, so you can never call, if you say this argument is a type never, then you can never call it. That one there. And you can also say this function is going to return a string or none or something else. So it's like sets of types or unions of types it supports. Okay. Any questions?
What is the purpose of never? Sorry, I stopped you there.
The purpose of never. Now, I have seen some examples of that. So returning never makes sense if you've got a function that's always going to say throw in exception. So the return type of that function would be never, because it's never actually going to return. If that makes sense.
Or
Yeah,
is it-
yeah. It's probably less useful being passed in as a.
Or can you just make it void?
So you can't even say it's equal to that, and it's because it's. Yeah. I don't know. I'm not a great Python expert.
I've never
Yeah.
worked with Python, so I have no idea.
Yeah.
There's just
It's never an inbuilt type.
Well, it's
Well, it has
built
to
into
be.
the type checker. Yeah. Same as in TypeScript as well. Has never.
I was going to ask a question about, you said that the compiler doesn't know anything
Yeah.
about types,
Correct. Yeah.
but there's tons of types in the file, so how does it know to ignore the stuff about types?
It just strips them out. Yeah. So it's.
So it does know about the type, but it doesn't care about the type.
Yeah. Yeah.
So if you try to compile it on an older version of Python which didn't know about types, it'd just blow up and say, what's this crap from the file?
Yes. Yeah.
So it kind of does know about types, but doesn't know how to check the types.
Yeah. Yeah. Same as the proposal for JavaScript is saying about adding support for types into JavaScript. In that, it will just ignore them and not do anything else with them. Okay, so now on to C#, which we all know about. So. So it's a different combination of keys to zoom in and see. Right. Yeah, can you read that, or shall I make it bigger still? Make it a bit bigger. So you can probably skip over a lot of this because most of you probably know C#. So in C# we've got you've got type constraints on the generic things, so you can be quite complicated. So I'm saying that my generic type T1 has to implement that interface and has a parameterless constructor, and type T2 has to implement, or has to be inherited from T1. So that's quite complicated. So C# also has the concept of nominal typing. So there's two types of typing: there's nominal typing and structural typing. So nominal typing means things that are matched by name rather than the structure of the stuff. So what I mean here is I've got two classes which have both got a single property of type I. So they've got the same structure, but you can't use them interchangeably. In other languages such as JavaScript and TypeScript you can, because they look the same, so that's fine, so you can pass either of them. So this is nominal typing. So the way in C#, as you're probably all aware, you'd have an interface instead, and that interface would have that type, and they'd both inherit from that interface. So again, so types in C# and other languages split into value and reference types. How much? Yeah. So. So you've got reference types. So maybe we should start with value types. Okay. Okay, so the way reference types work is when you declare something such as an array or a string or an object, so you've declared them in a function, then in the stack for your function, you just have a pointer to where that type lives in the heap outside of your function. So when I've declared a variable of types, and I've got an object, sorry, a class of C, and I declare it in my method, then that's a pointer to where it lives on the heap. And the class itself then contains integers and strings. So value types, when you declare them, so if I declared a integer, equals 10. So then that's declared locally, so that lives on the stack within that function. Does that make sense to people? Not a particularly good explanation, I'm afraid. But the class itself can also contain integers and strings, and they are also on the heap because that object lives on the heap. So the definition that value types live on the stack and reference type lives on the heap is not the correct definition, is what I'm trying to say here. Can you explain this better, Kevin? Oh, I've lost it. Yeah. Yes. Yeah. Okay. So the important point though, and then you've also got structures. So structures are more like value types, so they will live on the stack within the function. And because they're the actual values themselves, these can never be null, whereas a class can be null. So you can have a variable type C that's pointing to a class, but that class can be null. You've got a structure that can't be null because it's actually living on the stack itself.
But if you've got a structure and an object, then it's on the heap again.
Exactly, yeah. And you can also make things such as arrays. You can say, actually, it's going to be on the stack locally as well.
Have you ever used that?
Only in some advent of code problems. It's really trying to squeeze out some performance. But not normally, no. Okay. So the point of this, this made more sense with the C++ groups. So the point is some things can be null and some things can't be null. And the way you handle nulls in C#, which I expect you've all seen, is you can use question marks and nullability. And then the IDE is clever enough to know whether something can possibly be null in your method. So here, hopefully you can see, I've said B can be null. And so if I do b.length, you can see that there's a red line underneath because the IDE can't prove whether it's null or not. And then you can use the exclamation mark which says, I know it's not null. And then it believes you from then onwards. And so that does flow analysis within the IDE to work out whether something is null at various points. And then that gets more interesting when you've got something like a dictionary where you do dictionary, trying to get the value out of a dictionary. So if the value 123 is a key to the dictionary, it populates the variable v. If it doesn't, then that's going to be null. But the IDE knows whether it's null or not still. So here it lets me do v.length because it was in the dictionary. But down here, there's a squiggle underneath that v because it doesn't know whether it's in the dictionary or not. So the IDE is clever enough to know, depending on the result of calling that function, whether or not v is going to be null. And the way it does that is, if you look at the implementation, where is it? There's an attribute which helps the IDE, which says this thing may be null when the return code of this method is false. So that's how it knows. Does that make sense to people? Good.
Wouldn't the area out now because it's declared outside the loop?
That actually,
is outside.
it does actually work down here. You can, yeah.
Yeah, it actually declares the actual variable outside of it.
Yeah. Yeah.
It's like you declared it within the void method above it.
Yeah, but you're right, that sort of was catching me out thinking, can I write it down here? Because otherwise it's like, what would happen if you declared a V down there? It would be a bit strange.
The string is a funny example, isn't it? Because it can be null, you don't have to use a question mark, it can be null anyway, can't it?
Yeah. Strings are a bit funny generally, aren't they? So. Okay.
Nullability in C# is different to all the other typing, isn't it? Because it's only typed by attribute. It's not kind of not built in like the rest of the types.
Unless you use like nullability for value types. Which
Yeah,
then behaves
that's a
differently.
totally different implementation.
Yeah.
So nullable value types are actually a type, but nullable reference types
Yeah.
are just some annotations.
Yeah.
String is just an object, isn't it? Yeah. It's just in fact it should have the word string.
Yeah.
So you call it a type, wouldn't you? So
Yeah. Yep, so type aliases, you can do type aliases in C# as well. So you can set up your own alias up here, which I've done a few times. So here I'm back to that similar example with Python where I've got an address ID and a name ID, and then I declare my function down here, which takes an address ID and a name ID. And then I'll try calling it both ways around here. And then again in C#, it's quite happy. It will let you call them back way, the opposite way around, because all you're doing here is you're just saying, this is just another name for integer. It doesn't do anything beyond that. So it's not a new type, it's just, it's just an alias of that name. And then I came across this f-bounded polymorphism, which I thought I had to include, which is where you've got a type constraint that refers back to yourself. So here I'm declaring an interface called iFluent interface with types in a T, and I'm saying that T is of that type. So it's like a recursive. And Kevin assures me there are many good uses for this. So.
Is that a good example there?
Yeah.
It's quite good when you've got like a template passing in, but the thing inside of it is actually creating the object that you're passing into it. Because then it knows how to create it and then pass it to its template.
I just thought it was good because it's called F-bounded polymorphism. So that's, yeah.
I didn't even know it's called.
Yeah. My slides just. Okay, so then we've got.
You can use that time stand up now if you're talking about it.
Yeah, I think we should use some F-bounded polymorphism. Okay, so then we've also got its sibling of F#. So who here's done any F# in the past? None, okay. Okay, so F# does lots of type inference. So here I'm declaring a function called add, which takes in two values, a and b, and then returns their result. And if I move the mouse over it, yeah, so you can see in the tooltip there, it's inferred the types of taking in two integers and returning an integer. And it knows those types because I've called it here with those values. So I've said result is adding 1 and 2. So if instead of calling it from here, I call it down here with you can see now, because I've called it with float numbers instead, it's changed the type signature. So it's made it less restrictive. So it's doing the inference based on how it's called. And then down here, for example, I've got an identity function where you pass it an x and it returns the same value. And so it knows its type is a generic of A, and it returns the same A. And so it's quite happy to let me pass in 1 or hello as a string. So one of the nice things you've got is something called type providers. So here I've taken a CSV file called people, and then I'm mapping over all the rows in that CSV file. And if you notice here, I've got the name of one of the fields in the CSV file. And if I dot that, you can see it lists all the names of the columns in the CSV file. So I can pick H, for example. And if I go and look at the CSV file, which is where's it gone? People. And let's say I rename age to be I don't know, year. So all I've done is change the CSV file. If I go back to my program now, you can see it's now picked up the new type name in the IntelliSense. So it's getting its type information from an external source as part of the IDE. So it doesn't have to just be a CSV file. You can do database lookups and all sorts of things at this point, which is quite cool.
What would have happened if you left it as age?
So it compiles fine if you left it as age, but at runtime, because I've given it a file which doesn't have the age column, it will just break at that point. It's the same as if you've written a database query in your program, and that column doesn't exist in your table when it runs.
This won't compile now, though.
No, it won't compile now. No, but
if the provider
yeah.
doesn't have it compiled,
Yeah.
it'll not compile.
Yeah.
But if the CSV switches the types out, the fields out at runtime.
Yeah. There you go. Yeah.
But if we hadn't changed it, let's say it says we change it to year,
Yeah.
and then CSV back to age, it would compile, wouldn't it?
Yes, it would.
Without doing any changes.
Yeah, it would compile like this, and then at runtime, if I gave it a file with the age in instead, it would then break at runtime. Yeah. Yeah, so it's a bit like you rename a column in Entity Framework, for example. You do the same. Yeah.
After we renamed it, age was right, right?
Yeah.
Which is obviously the case that doesn't exist, but
Yeah.
before you changed it,
Yeah.
it wasn't.
Oh, okay. Yeah. Yeah, so I think we'll see me. I mean, if I change it back to age now, it won't immediately. yeah, it doesn't immediately spot that it's not valid. I don't know. I don't know if you close and reopen it. Yeah, I don't know when it redoes it. Yeah, we'll see you make a change. Yeah. I still think it's pretty cool though. Okay, so yeah, one of the things F# does have is something called discriminated unions. So a discriminated union here is that we've got a type, and the type can be of various things. So it's a bit like an enum, but we've also got additional information about each entry in there as well. So rectangles have got widths, and circles are radiuses, and prisms have got widths, something else, and a height. And then we can create objects of variables of type, rectangle, circle, prism, and then we can match on them using pattern matching in here as well.
So it would like switch stuff, right?
Yeah, it is. Yeah, it's like in C# when you do pattern matching on the type of a class, but it's just sort of cleaner syntax, I guess.
Well, looks better.
Yeah. Okay, so back to our idea of having customers and address names. So again, I've created some new types here: customer of type integer and address. And I've got my functions which take them in as arguments. And then see, this time we do actually get an error if we try and call the method the wrong way around. Because these aren't aliases; these are actually new types which just wrap up a single other type. So this is a wrap around an integer in effect. So this would solve that problem. You can say something?
We can do that in C# with a read-only record struct.
Yeah.
Whatever it is.
Yeah.
With just an int as the constructor.
Yeah. So F#'s got generics. So I've got my class here, which has got a generic parameter of type T. And you can also you can be quite clever. You can say T can be anything, but it's got to have a property in there called property 1, which is an integer. So you don't have to have an interface. You can just define it directly in there. Okay. So methods. So back again, I've declared some functions. So I've got this function f1, which takes in an x and returns x plus 2. And I've got a second function. What was I going to show here? Oh yeah, f2, which takes in a y and passes that to f1. And then that all compiles fine. But if I take this function and put it above this one, it no longer compiles. So because the inference is so rich, it has to do things in order. It has to go top to bottom down the file. So it doesn't know what f1 is at this point because it's declared further down in the file. So then you think, well, what happened to something like recursion? Because that can't compile because we haven't declared the function yet. So because the Fibonacci function uses Fibonacci itself in order to run. So if you've got a recursive function, you have to explicitly say it's going to be a recursive function in order for it to know.
So what happens if you say something's recursive when it's not? Can you put the second function above the top one and tell us it's recursive?
I don't know. Yeah. No.
It's not declared within it, is it? There's the bottom one declares the function, and the fib is within the function and the bottom one.
Yeah.
Whereas it's not the equal sign is what makes that work. I think.
Which I guess is a big contrast to like JavaScript where everything is hoisted to the top.
Yeah. Okay, so then we've got another file. So this file we'll look at here is called order.fs, and we also got an order2fs. So module 7, and we've got a function in here called hello. So if you just go back to our first one. So down here I'm going to import that second module, which was called example 7, and use the function from it. So the problem here is it can't find that function in here, even though it's in that module, example 7. It can't find that, and so it can't call the function. And the reason for that is it's the same thing in that the files has to be in the correct order. So if I rearrange the order of files, so it compiles this one first, then it will find that function. So not only does it have to be in the correct order within your module, the modules have to be in the correct order in the project. Does that make sense?
Is that not just a file system then? Is that special?
Yeah,
ID or?
yeah. I assume the project file has the order of the
Okay. Yeah.
files in there, does it? Yeah, it must be these includes. Must give it the order. Yeah. So the first time I did F#, that caught me out because I couldn't understand why it couldn't find half my functions. And another nice feature in F# is units of measure. So you can say something's a unit of measure, like a kilowatt hours, or pounds example, and then that catches bugs like adding pounds to hours and things like that, because you've got a unit of measure. But you can understand that you can divide things by another unit of measure to get something else, like miles per hour and so on. So that's quite a nice feature of F# as well, to help eliminate bugs. Any questions so far? Good. Yeah, so there's probably not much to say about Lisp, I don't think. Yeah, I don't know if any of you've ever done Lisp before. It's a very sort of powerful language, but I think we'll skip over that. You can define your own types in Lisp, and you can define functions that check whether a type is true and things like that as well. So it's quite clever, but I think PHP. Okay, yeah, so I don't know much about PHP. I don't know many people have done PHP here. So this is one of those languages that traditionally has had a very bad reputation in terms of sort of quality and bugs and things, but it's got a lot better recent versions. Oops. So before, it used to be things like you define a variable as an empty string and subtract from it and print it out, and it'd say it's an integer. And you have bugs like that. And with PHP 9 onwards, that type of thing is now a compile error. It does have things like union types now from PHP 8 onwards, so I'm saying number there is either an int or a float. But it can't be like not a number, for example. Yeah, and you've got interfaces and so on. So modern PHP is a lot better than it used to be. Okay, so some TypeScript now. So how many of you use TypeScript? Yeah, good. That's not right. Yeah, so I don't know why my ID always shows the first thing as being an error. Ignore that. Yeah, so as I was saying before, so TypeScript has structural typing rather than nominal typing. So it means here I've got a person which has got a name and an age, and a human which also has name and an age, an adult that has name and an age, and you can pass all of them to our print person thing because the human has all the things it needs to make up that person type, as does an adult. So you don't need to use an interface, it's got the right fields or properties. Human.name. What does that mean? Oh yeah, so it's not duck typing because duck typing only gets checked at runtime. This actually happens at compile time. So because I've removed the name from human, you're getting errors in the IDE. So it's structural typing rather than duck typing. So TypeScript basically looks at types as being sets of things, really. So here I've got a set of dark colours and a set of light colours, and then I can union those two sets together to get me another, a bigger set of colours. And so black and white are valid in my print function because one's a dark colour and one's a light colour, but purple's not in either list, so that's not in that set of colours. Yeah, and then I've got a function here which takes in a union of types, so it can be either a number or a string, and then I can quite happily call it with either of those, but not a Boolean. So this looks like you could probably do discriminated unions, similar to what we were looking at before. So before we had the shapes as the example, so here we've got some network states, so loading state, or we've got a fail state which has a code, or a success which has got a response, and so on. And then our type is the union. The type is, the or those three possible states. But the problem with TypeScript is we can pass that into our function, but within the function we don't actually know what type it is, because the way TypeScript works is when at runtime it strips out all the types to give you plain JavaScript. And in JavaScript it doesn't have a concept of any of these types at all. So it doesn't know what this response is, and so you can't just have a case statement. I think, if I remember correctly. Yeah, my CD into that folder. Yeah, so that should have generated me some. Yeah, that's the wrong folder, isn't it? I was going to show the JavaScript, but I won't. Yeah, so the JavaScript is just the same as this, but with all the types stripped out, so it can't tell what type of network state it is. So the way you can get around that in TypeScript is you can have these extra functions where you give it an object and it returns true if the object is of that type, and it does some check within there. So we know it's a network fail state if that type has has a code property, and we know it's a success if it's got a response property, and if it's got neither of those, we know it's a loading property. So it uses this state is thing. And then down here, you can then use that in the function to work out what it is you've been given. Does that make sense? So the problem here is you have to write a function for each of your different types, and you have to have some way of telling these objects apart as well. So if they've all got the same properties, you can't do that. So the more common way to do it is you add an extra field, which maybe called kind or a state, which actually just tells you what it is. And then you can just check that in your code instead. So that's the more common way of doing it. So it does have discriminated unions, but not as good as the ones in F#. And then you've got some really weird, fancy stuff as well, where you've got methods where you give it a type, and it can do a transformation on it to create another type. So, for example, read-only and partial. So you give it a type of person, and then it returns another version of that type where all the fields are now read-only and also optional. And then you can use that to build up on other types and get really complicated. So here, for example, I've replaced all the string fields with Boolean fields and so on, and renamed them. So you can do quite a lot of sort of fancy manipulations on types. I don't know if anyone's ever actually done any of that in real life there. Yes.
Use partials, but I've not seen changing the types.
Yeah. So you can check to see what type it is by using extends, and then capitalise, puts a capital letter at the front, and so on.
Have you used pick and omit?
Okay. Yeah.
So if you've got like a type which is a person, like a view of a person, and then also an editable person, you get the editable one and then omit the ID or something to give you as the normal person, which has not been created yet. For
Yeah.
example.
Yeah. And you can also use the never type as well to, yeah, so if you're union two types together, you can use never to make sure you only pick one of them and things like that. So what else? Oh yeah, so TypeScript, you can also add your own types to existing JavaScript libraries that don't have types by creating an extra file with sort of the declarations in. So we do this at work because we use D3 and there's a few types missing, but you can just declare them yourself. And that's fine. And then that's you can do that in Python as well, where you can just declare the types for existing libraries. Right. How am I doing for time? 8:05. Okay.
25 minutes away.
Okay.
10 languages in.
Is that what? Okay.
2 minutes per language.
We can vote on the languages.
Yeah, should yeah. Done that one. TypeScript. What languages? Yeah, Ruby. There's not too much to say about Ruby. Again, it's dynamically typed. And until recently, they had no concept of type checking at all. But they've just got some third-party tools recently, and they have its own language. So you declare the types outside your source code and check it. But it's not very widely used at the moment. Yeah, you've got SQL Server or T-SQL. So that's obviously got primitives in it because it's got different column types such as varchars and numbers and booleans and so on. And you've also got tables which are a bit like types, but it does actually have type aliases as well. So in SQL Server you can say money is, in this example, a varchar 11. And you can create your own name types. So here it look a bit like tables really. And you can also create custom types based on C# code and external libraries and load them in as well. So yeah, SQL Server definitely supports types. Now HTML, so originally I was thinking HTML doesn't have a concept of types, but then I sort of changed my mind because I think all elements are types really in HTML. You've got like head, body, section, and so on. So they're all things which are giving you information about what it is you're describing. So that's really all a type is. So in this example here, I've got a block quote, so you know it's going to contain a quote. I don't think class names particularly give you any extra information about it though, because a class name, this is a Tailwind example of some sort of styles it's applying. So that doesn't tell you anything other than, well, I mean, we know that means margin and padding, but that doesn't really mean anything about the content of it. CSS, it has custom properties. So here I've got a custom property called main background color, which I'm set to brown, which you can use further down. But you know, if you set it to an invalid value, it's just ignored. So it's not really any types. It's just very basic properties. Bash. So Bash does sort of have the concept of types in that on the command line you can declare a variable, you can say it's sort of type integer, or you can say it's an array, but it doesn't really have much support. So I think we'll skip over that. Okay, so Rock is a new language. Has anyone heard of Rock and Rocklang? No, I've got to remember what it was I was going to demo in this. So yeah, so Rock was been written. It's a new language. It's not actually even in sort of beta release yet, but it's designed to give as much information to the developer using types as it can. So starting at the top, one of the things is you say the platform it's going to run on. So it can run as like a console application or a web application or a mobile app, and then it only has access to those things. So from a security point of view, it's good because you can't access anything outside of that world. So if you're saying it's a console app, then you've got no access to web stuff. And if you're saying it's a web application, then you've got no You can't write to the console, for example. And so you can use it as a plug-in language for other tools as well, so you can really restrict what users can do in that language. So that's the idea of a platform. And again, you've got inferred types. So here we're creating a function called complete name, which takes in 2 arguments. So it's worked out they're strings, and the thing it's going to return is a string. So that's our function definition. So a bit like F#, it's inferred all that. But you can also add your own type annotations if you want on the line above. And then you've got generics as well. So we've got like a list of anything. So star can mean anything, or you can name them. So we've got something called backwards, where I give it a list, and it returns a reverse of that list. And you can build up unions of types as well, a bit like in TypeScript, where I've got color from string, where I give it a string, and it's going to return either red, green, or yellow. And you can see that the tooltips are very rich, and it gives you a lot of information about errors and things, and tries to be as helpful as possible. What else was there to say about rock? Yeah, so you've got a concept of opaque types. So here I'm saying a username wraps over the top of a string. So, and then within here, within my method, well, within that module, you can then convert things from strings back to usernames and vice versa, using this sort of method, which gets the internal value out. But to the outside world, that just then looks like a new type. So this would solve our custom ID, name ID problem we saw before. I think we'll probably, I'll probably skip over all that. Yeah, so Rock looks like a good, interesting language, and it's it'd be interesting to see it when it's released. Right. Haskell. Has any of you done Haskell before? So Haskell's a very functional type-rich language. So it's a bit similar to F# and Rock we've just seen, where I've defined a function here called add3, which takes in an x as an argument and returns x plus 3. So its type signature takes in an int and returns an integer. A good example of this. Yeah, so a map. So this is like select in C#. So you give it a list of things. You give it a function which does something to each item in that list, and it returns a list of the other thing. So if you imagine you had a list of strings and you had select int.parse, so that method there would be int.parse. So it would take in a string and return an integer. And then you're calling it on a list of strings, and it returns a list of integers. So hopefully that makes sense. So that's what that sort of signature means. So that's the first argument, and that's the second argument, and then that's what it returns. Which brings us on to something called kinds. So at the start of the video, we saw Simon solving the Sudoku problem by by going a level above. So we started off with numbers, and then he started solving it using colors instead. And if you think of types and values, types are sort of the same thing to values, where you've got your integers and you've got your strings, or you've got a generic type, which is like the level above that. So it turns out you can actually go a level higher than that still, and that's called a kind. So a concrete type has a kind of a star. So that's like a string or a Boolean. And then you've got type constructors, which are generic things such as a list of T. So a list of T isn't a type, it's something that constructs a type. So you have a type constructor, which is a list of T. You give it an integer, so you give it a value of T, which is an integer, and it gives you back a list of integers. So your type there is the list of integers. So that's written like this. So it's written, you give it an integer, and it gives you back the list of integers. So that's the kind of that. Yeah, so then you can do things such as, so imagine that you had a function which you gave it a list of t, and it returned a tuple of that type. So you gave it a list of strings, and it returns you a list of tuples of strings. So a list of, I don't know, David, Kevin, and it return the first entry would be David, David, the next entry would be Kevin, Kevin. So it's duplicating them all up. So that would look like this. So you give it a function's called double list. You give it a list, and that's what it gives you back. And you could do the same thing with an array. You give it an array of t, and it returns you an array of tuples of those things. Or you could have a tree, okay? So they're all doing the same sort of idea in that it gives you a single t, and it returns you back the tuple of them, okay? So if you look, they've all got the same signature. The only thing that's varying is this bit on the front here. So that's sort of an extra level of kind again, where you're actually passing in different generic containers to the same method. So that's not something you can do in C#, but that's something you can do in languages like Haskell, which have higher sort of type systems. Don't worry, you don't understand it all. That's just sort of just a rough overview of what you can do.
I'm curious, what about dictionary?
Yeah, so a dictionary is the same sort of, so you could have key to value, and the values could be the same sort of thing. Yeah.
So if you feed the dictionary, it would become double dictionary?
Yeah, so if you had a dictionary of, say, int to string, it could do int to string, comma, string. Yeah.
Okay.
Yeah. Yeah, and so so that's what its kind signature would look like. This in this case is what the point is. So the idea is just to know that you've got values, then you've got types, and then there is something that exists called kind, which is higher still. And then closure. So I saw this talk by Rick Hinckley when I was preparing this talk, and so I don't know whether he wrote part of closure, but he's certainly sort of part of in the design of it. And Clojure is a dynamic language that doesn't have any typing hints or anything like that. But it does have a language called spec, which uses define what data looks like. So in this example here, we're saying a make is a string and a model is a string, and a year is an integer, and also it has to be bigger than 1900, and a computer's made up of a make and a model, and so on. So you can define what your types, what your data looks like. So that's spec. So, and one of the points he makes is things such as optional types in languages like F# are probably wrong, or in his view are wrong. So here we've got a method called calculate, where I pass in a integer, and it returns something that may or may not be null. So options like null in F#. So I'm giving it a definite integer of A, a definite integer of B, and it returns a nullable of integer. So when you call that code, you can pass in 12, 34, call calculate, and you have to do pattern matching on the result because the thing that comes back can be null. Okay? Does that make sense to everybody, roughly? So it's just like you can never access something that's null because you have to match it first. And if it's null, it'd be none. So he makes the point, well, this is all very well and good, but what happens if I make this function less restrictive? So instead of saying A always has to be provided, I'm going to say actually A can be null. And also I know I'm always going to be able to return the result. The result is no longer nullable. So my function's less restrictive, so it should be easier to use now, not harder. So his point is now, so why do you then have to change the code that calls it? Because before I can't just pass in an integer anymore. I have to say it's something that can be null, which you have to do sum. And the result I get back is no longer a nullable integer. It's now always an integer, so I have to change. So I can't use pattern matching on the result that comes back. And so his point is because option shouldn't really be a type like that. Option should really just be a union of numbers and null. And you shouldn't think of it as a separate type. So another point he makes is if you've got a function signature here, so I've got a function called reverse where I give it a list of things and it gives me back a list as well. It doesn't tell you anything beyond that. It tells me that I've got a list of the same type, but this function signature doesn't tell me I've got the same number of items, for example, or they are the same items. So it's not actually giving you very much information at all. Yeah, so it's quite a good talk. It's worth watching. So then, yeah, so the next question is, why would you ever want to write dynamic code? Because I've shown you all the advantages of using types. And one of the reasons is, so this is a real world function signature I've got in my code at work, where it's a minimal API, and it returns a task, and it's going to be all these different results. And now I've got all these inputs to it. To write the same thing in Python without any typing hints is just one line. It's obviously a lot quicker to write that. So your trade-off there is simplicity against all this extra type checking. So maybe it depends on how long your programs now live for, whether or not it's worth having all these extra checks. And so finally, just a final TypeScript example.
Having types like that allows you to generate other things there, right?
Yeah.
So like in the minimal APIs example, from the types you can start generating open API specs or other clients in different languages, etc.
Yeah. I mean, personally, I'm all for types. Yeah. I'm not all for Apple Macs. Yeah. Yeah. Well, it was compulsory at work, unfortunately. Where did I do it? I put the final file. Is it under end? Yeah. So here, someone's used just types to implement noughts and crosses, and so I've got a type here called tic-tac-toe, and I'll give it a board and some values, and then if I look at the type definition, yeah, so okay, yeah, so that one's a game that's in progress. So this one here is invalid because I've got an X and a naught in the same row and cell. So if I move my mouse over it, the type's actually telling me that. This one down here, X actually wins. So the type actually returns X wins, and it's a draw, and so on. So this is all done just using the type stuff we saw before in TypeScript with extends and creating new types and so on. So it's obviously quite powerful. Yeah, so the whole game is just in. Well, yeah. So then, if I change that, for example, then it's no longer invalid. And presumably if I put something that's not yeah, we can't even compile that. Yeah, so obviously, it can be quite powerful in the type system. And that's it. That's finished early. There we are. 8 minutes to spare.